You can't actually see it happening. But in a power plant, it's going on all the time. Chemical energy in the form of fuel is continuously being converted into electrical energy. Electricity to supply consumers with their electrical needs. Energy in, energy out. But the amount of electrical energy that a power plant produces depends on the efficient operation of all the components in the plant cycle, and how efficiently those components operate is known as plant performance. The process in which chemical energy in the form of fuel is converted into electricity within a power plant is a complex one. The more fuel that it takes for a plant to provide a given amount of electrical energy, the more it costs to operate that plant. So, it's important that a plant operate at its highest possible efficiency so that the least amount of fuel is used and costs are kept to a minimum. In a power plant, chemical energy is first converted into thermal energy. The thermal energy is then converted into mechanical energy, which in turn is converted into electrical energy. Now ideally, all of the chemical energy put into a power plant in the form of fuel would be converted into electrical energy, but that just doesn't happen. A large amount of energy is lost in the processes that take place within the plant cycle. The result is that the amount of electrical energy that comes out of a plant is much less than the amount of chemical energy put into a plant in the form of fuel. Even though much of this energy loss is unavoidable, the way a plant is operated is the most significant factor in determining whether as much electrical energy as possible is produced. It's an important part of an operator's job to see to it that his plant produces electricity as efficiently as possible. How well a plant's components operate to produce electricity is called plant performance. And in this unit, we're going to talk about plant performance and how it's measured. We'll also discuss some of the things that can affect a plant's performance. The performance of a plant is carefully monitored and kept track of. Temperature and pressure readings that you, as an operator, take and record daily are used to measure and determine the overall performance of the plant. Plant performance is most commonly measured in two ways, by efficiency and by heat rate. The overall efficiency of a plant is a measure of the amount of energy going into a plant compared to the amount of energy going out of a plant. A plant's overall efficiency is usually expressed as a percentage. For example, if the amount of electrical energy going out of a plant is half the amount of chemical energy that's put into the plant as fuel, the plant would be operating at 50% efficiency. If all of the chemical energy put into a plant was converted into electrical energy, then the plant would be operating at an efficiency of 100%. Although a plant's ideal goal is to operate as close to 100% efficiency as possible, the amount of electrical energy going out of a plant is never as great as the amount of chemical energy put into a plant. So, a plant is never 100% efficient. In fact, the normal loss of energy in the plant cycle is high enough so that a typical plant operates at about 33% efficiency. In other words, about 67% of the total energy put into a plant does not go out of the plant as electrical energy. When a plant is designed, the energy losses that occur in the plant cycle are taken into consideration. Each plant is designed to produce a certain amount of electrical power while consuming a specific quantity of fuel. But when components don't operate at their best, more fuel is required to maintain the same energy output of the plant. For example, let's say a plant is designed to have an electrical output of 160 megawatts while consuming 66 tons of coal per hour. If the plant's efficiency decreases, it would take more coal to produce the 160 megawatts. As the efficiency of the plant decreases, the amount of fuel required to produce electricity increases, and with this increase, the cost of operating the plant also increases. Therefore, the performance of a plant is carefully monitored so that decreases in efficiency can be easily discovered and efforts made to correct problems and restore efficiency to normal. Now, heat rate is another way to measure plant performance. Heat rate differs from efficiency in that efficiency, as we mentioned before, is expressed as a percentage. Heat rate, on the other hand, is a direct measurement of the amount of chemical energy required to produce each kilowatt-hour of electrical energy. Heat rate is measured in units of BTUs per kilowatt-hour. We're going to talk about heat rate, how heat rate is calculated, and some of the things that can affect the heat rate of a plant. But before we do that, review the information we've given you so far in your text, and if you have any questions at all, be sure to ask your instructor. As we mentioned earlier, the energy losses that normally occur during the plant cycle are considered and accounted for in plant design. Heat rate is one of the factors established in the design of a plant, allowing plant performance to be monitored during normal operation by comparing the actual heat rate to the design heat rate. In this segment, we'll talk about how heat rate is calculated during plant operation and some factors that could cause variations from the design heat rate. Keeping track of heat rate in a plant is very important. Heat rate is a direct measure of the amount of energy it takes to produce each kilowatt-hour. And by keeping track of a plant's heat rate, we can determine whether or not a plant is performing as efficiently as possible. As we said earlier, heat rate is expressed in units of BTUs per kilowatt-hour. BTUs are units of energy, and as it applies to a plant's heat rate, BTUs are used to express the amount of chemical energy contained in the fuel put into a plant. Now, the BTU content, or heating value, varies between different fuels. The heating value of the fuel used in your plant is an important quantity, as it is a measurement of the amount of energy in the fuel. So, samples are taken of the fuel before it is put into the boiler in order to determine its heating value. In addition, different types of fuel use different units to express heating value. For example, the heating value of coal is expressed in BTUs per pound, while the heating value of natural gas is expressed in BTUs per 1,000 cubic feet. For our discussion, we'll assume the fuel the plant is using is coal. So, the heating value in BTUs per pound, along with the amount of fuel consumed per hour, are used in conjunction with readings from electric meters that record the amount of electrical energy produced per hour in kilowatt-hours. These values are used to calculate an overall heat rate for the plant. To calculate a plant's overall heat rate, the formula used is heat rate is equal to the fuel burned in an hour, or any specified amount of time, in pounds, times the heating value of the fuel burned in BTUs per pound. This value is then divided by the net electrical output, or net generation, in kilowatt-hours. Let's take a look at an example of how to calculate the heat rate for a typical plant. The plant we'll use as an example is currently using 134,000 pounds of coal in a 1-hour period. The heating value of the coal being used is 12,500 BTUs per pound. 168,380 kilowatt-hours are being produced. To find the heat rate of the plant, we must substitute these values into the heat rate formula. First, we multiply 134,000 pounds times 12,500 BTUs per pound. With this calculation, we get a value of 1,675,000,000 BTUs. To complete the calculation, 1,675,000,000 BTUs must now be divided by 168,380 kilowatt-hours, which equals 9,948 BTUs per kilowatt-hour. So, the overall heat rate for this plant example is 9,948 BTUs per kilowatt-hour. Up to this point, we've considered heat rate in terms of a specific amount of time. However, there is another way of calculating heat rate. This formula is used to find heat rate at any given moment and is based on the fuel consumption rate, heating value, and the rate of electrical energy production. The equation is heat rate equals fuel consumption rate in pounds per hour times its heating value in BTUs per pound divided by the rate of electrical energy production in kilowatts. Considering the same plant as we did before, the known values can be substituted to find heat rate using this equation, and we should come up with the same answer. 134,000 pounds per hour times 12,500 BTUs per pound divided by 168,380 kilowatts. In the numerator, pounds cancel, and we're left with 1,675,000,000 BTUs per hour. Dividing by 168,380 kilowatts, we get a heat rate of 9,948 BTUs per kilowatt hour. The heat rate remains the same. As we already mentioned, each plant has a design heat rate. If a plant is operating properly, the heat rate calculated from the information recorded in the plant should be about the same as the design heat rate. The design heat rate for the plant in our example is 9,948 BTUs per kilowatt hour. The heat rate that we calculated was also 9,948 BTUs per kilowatt hour. That tells us that the plant in the example is operating at its design efficiency. But let's suppose that the heat rate that we calculated was greater than the design heat rate for the plant. An operating heat rate that's greater than a plant's design heat rate indicates that for some reason the plant is not operating as efficiently as it should. There are many reasons why a plant's efficiency may decrease. One possible cause of inefficiency in a plant is a change in the temperature of superheated steam entering the turbine. As you probably already know, a turbine is designed to operate most efficiently when it's supplied steam at a specific temperature. So, the temperature of superheated steam must be maintained as close as possible to the temperature at which the turbine is designed to operate. A decrease in the temperature of superheated steam causes an increase in the heat rate of a plant. If the increase causes the operating heat rate to be greater than the design heat rate of the plant, then a plant operates less efficiently. In general, if the temperature of superheated steam increases, the heat rate of a plant decreases, and the more efficiently the plant operates. But if the temperature of the superheated steam should increase too far above the temperature at which the system is designed to operate, damage to the system's components may occur. A change in condenser vacuum also affects the heat rate of a plant. When condenser vacuum decreases, it causes the turbine to operate less efficiently because less energy is removed from the steam passing through it. So when condenser vacuum decreases, heat rate increases. In other words, less electrical energy is produced and the plant's efficiency decreases. On the other hand, generally the greater the vacuum in a condenser, the more efficient a plant's operation and the lower the heat rate will be. Besides the temperature of superheated steam and condenser vacuum, feed water temperature also has an effect on a plant's heat rate. Feed water heaters are used to increase the temperature of feed water before it enters the boiler. If feed water enters the boiler at a temperature that is close to boiling, less energy is needed at that point to change the feed water back to steam. In general, the higher the temperature of the feed water, the lower the heat rate of a plant, and the more efficiently a plant will operate. Also, the lower the temperature of feed water, the higher the heat rate and the less efficient a plant operates. The temperature of superheated steam, condenser vacuum, and feed water temperature all affect the heat rate of a plant. And maintaining the correct superheated steam temperature, the correct condenser vacuum, and proper feed water temperature are extremely important to the efficient operation of your plant. As an operator, it'll be your responsibility to help ensure that the components in your plant cycle are operating as efficiently as possible so that your plant can maintain its heat rate as low as possible. Before we go on with our discussion of heat rate, take a few minutes to read through the material in your text and answer the questions you'll find there. In the last segment, we talked about the overall heat rate of a plant, and we showed you how overall heat rate can be calculated. To calculate overall heat rate, we had to know how much energy in BTUs was going into a plant, and how much energy in kilowatt hours was going out of the plant. But besides overall heat rate, individual components in the plant cycle, or a combination of components in the cycle, also have a heat rate. You may ask yourself why it's important to find out the heat rate for individual components or a combination of components in the plant cycle. Well, problems in any of the plant cycle components affect the overall heat rate for a plant. So, Let's suppose that your plant's overall heat rate for this month is above the design heat rate. That means that there's an inefficiency somewhere in your plant cycle. But where? Let's take a look at this diagram of the plant cycle and see some areas where inefficiencies are likely to occur. The diagram shows the boiler, the turbine and generator, the condenser, condensate and condensate booster pumps, a boiler feed pump, and feed water heaters. One way to find out where an inefficiency could be is to isolate parts of the cycle and determine the heat rate for them. If the heat rate is too high for a portion of the cycle, then it's likely that the inefficiency is occurring in that part of the cycle. That part of the cycle can then be further isolated, and the heat rate for individual components can be calculated until the source of the inefficiency is found. In this segment, we'll isolate a part of the plant cycle for a plant that's operating at its design heat rate and calculate the heat rate for that portion of the cycle. Once we've established the heat rate for efficient operation in a portion of the cycle, we will, in following segments, illustrate how changes in operation have an effect on the heat rate of that portion of the cycle. Try to keep in mind that a change in the heat rate for a portion of the plant cycle will also cause a change in the overall heat rate of the plant. The portion of the plant cycle that we're going to look at has, as its major components, the turbine and generator, the condenser, feed water heaters, condensate and condensate booster pumps, and a boiler feed pump. Steam enters the turbine at this point. So, for this portion of the cycle, the amount of energy contained in the steam that enters the turbine is the energy in. We'll call the amount of energy entering this part of the cycle E sub S. The amount of electrical energy produced, or the net generation, is the energy out for this part of the cycle. We'll call the amount of energy out E sub E. But not all of the energy that goes into the turbine in the form of steam is used to produce electricity. Some of the energy is used to heat feed water in the feed water heaters. Some of the energy is lost when the steam is condensed back into water in the condenser. To determine the heat rate for the entire portion of the cycle, we must take the amount of energy contained by the water that exits the feed water heater into consideration. We'll call the amount of energy in the feed water E sub FW. A change of energy occurs between the steam entering the turbine and the water exiting the feed water heaters. So, in order to determine the actual relationship between the energy in and the energy out, we must find the relationship between the amount of electricity being produced and the change in energy in this portion of the cycle. To find the change in energy, we subtract the amount of energy in the water leaving the feed water heaters from the energy in the steam entering the turbine. E sub S minus E sub FW. Then, to find the heat rate for this portion of the cycle, we need to divide the change in energy by the amount of electrical energy produced in kilowatt hours. E sub S minus E sub FW divided by E sub E. Now, to calculate the heat rate, we'll substitute values into the formula for a specific amount of time. We'll use 2 hours as the time period we're going to examine. To find E sub S, we first need to know how many pounds of steam entered the turbine in 2 hours. For the 2 hours being considered, 2,340,000 pounds of steam entered the turbine. To find the amount of energy in the steam, we need to look up the enthalpy of steam for the temperature and pressure of the steam during that time. In this example, the temperature of the steam entering the turbine was 1,000 degrees Fahrenheit, and its pressure was 2,450 PSIA. We look up the enthalpy of steam for 1,000 degrees Fahrenheit at a pressure of 2,450 PSIA, and we find that every pound of steam contained 1,459 BTUs of energy. To find out how much energy entered the turbine in the 2,340,000 pounds of steam, we must now multiply 1,459 BTUs per pound by the number of pounds of steam. When we do this, we discover that 3,414,060,000 BTUs of energy entered the turbine in the 2 hours under consideration. This is the value for E sub S. To find E sub FW, we must go through a similar calculation. This time, we need to know how many pounds of water exited the feed water heater in the same 2 hours. For the time period under consideration, the amount of feed water flow was 2,340,000 pounds. As before, we need to know the temperature and pressure of the water that exited the feed water heater during the time period we're interested in, so that we can look up its enthalpy. For this example, the temperature of the feed water was 505 degrees Fahrenheit and its pressure was 2,700 PSIA. We find that there were 494 BTUs of energy in every pound of water. To find out how much energy was in the water leaving the feed water heater, we multiply the number of pounds of water that exited the feed water heater by 494 BTUs per pound. When we do this, we find that 1,155,960,000 BTUs of energy left the feed water heater in the 2 hours. This then is the value for E sub FW. Now that we have the values for E sub S and E sub FW for the 2 hour period, we need to find the value for the amount of electrical energy produced in the same 2 hours. 336,760 kilowatt hours of electrical energy was produced by this plant in the 2 hours we're looking at. We substitute that value for E sub E. To complete the calculation, we must first subtract the value for E sub FW from the value for E sub S. Our answer is 2,258,100,000 BTUs, which is the change in energy for this portion of the plant cycle. Finally, we divide the change in energy by the net generation, and we get a heat rate for this portion of the plant cycle of 6,705 BTUs per kilowatt hour. 6,705 BTUs per kilowatt hour is the same as the design heat rate for the plant in this example. That means that the components in this part of the cycle are operating at peak efficiency. Notice that this value for heat rate is smaller than the value of 9,948 BTUs per kilowatt hour that we calculated earlier for the heat rate of the entire cycle. This is because when we consider only a portion of the cycle, as we just did, inefficiencies or natural energy losses that take place elsewhere in the cycle are not compensated for. In general, when considering only a portion of the plant cycle, the value for heat rate will be less than it would be for the overall heat rate. So far, we've been talking about operation at the design heat rate. Next, we're going to take a look at what happens to the heat rate when the temperature of the superheated steam drops below the temperature for which the system is designed. For right now, though, take the time to review how to calculate the heat rate for a portion of the plant cycle. If you have any questions, make sure you ask your instructor. In the last segment, we calculated the heat rate for a portion of a plant cycle. The components in the cycle we looked at were operating at peak efficiency. So, the value of 6,705 BTUs per kilowatt hour heat rate for that portion of the cycle was the same as the design heat rate. In this segment, we're going to take a look at how a change in the temperature of superheated steam entering the same portion of the plant cycle affects its heat rate. As we said earlier, a turbine operates at its design efficiency when the steam entering it is at a specific temperature. A change in temperature above or below the normal operating temperature causes a change in heat rate. A change in heat rate for this portion of the cycle, in turn, affects the overall plant heat rate. Theoretically, when the temperature of superheated steam that enters a turbine increases above normal operating temperature, the system would operate more efficiently. But the system is designed to operate at a specific maximum temperature. If the temperature of superheated steam increases above that limit, serious damage to the system's components could result. So, any increase in superheated steam temperature must be kept within the operating limits of the system. A decrease in superheated steam temperature causes the heat rate of the system to increase. In other words, the system operates less efficiently, and heat rate for that portion of the cycle increases, and so does the heat rate for the overall cycle. There are many things that affect the temperature of superheated steam: blowing soot, the design of the boiler, and the common methods for control of superheated steam temperature are just a few. In fact, the temperature at which superheated steam leaves the boiler is dependent on so many factors that we can't go into all of them here. However, we are going to look at two common methods of superheated steam temperature control. Desuperheaters, or attemperators, are one common method used to control the temperature of superheated steam. As you probably know, a desuperheater is a device that sprays a fine mist of water into a steam line. This water absorbs some of the heat from the steam, thus lowering its temperature. The more water sprayed into the steam, the lower the steam temperature. In the control room, operators carefully monitor and record the temperature of superheated steam. And although the temperature of the steam is usually automatically controlled, on occasion it's necessary for an operator to manually control the operation of a desuperheater. Another way that the temperature of superheated steam is controlled in some plants is by burner tilts. The angle of the burners control the placement of the flame in the boiler. If the burners are positioned horizontally, the flame is placed like this. Some of the heat from the flame is used to boil the water in the water walls, and some heat is transferred to the superheater. If the burners are angled downward, like this, the flame also moves down. With the flame in this position, more heat is absorbed in the water walls, so less heat is available to the superheater. If they are angled upward, this way, the flame is closer to the superheater, and thus more heat is available to be absorbed by the superheater. Now, let's see how a decrease in superheated steam temperature affects the heat rate for the portion of the plant cycle we've been looking at. We'll calculate heat rate when the temperature of the superheated steam is 5 degrees below the turbine's design temperature. To find the heat rate, we'll once again use the formula E sub S minus E sub FW divided by E sub E. As you probably remember from our earlier discussion, E sub S represents the amount of energy contained in the steam that entered the turbine. E sub FW is the amount of energy contained in the water that exited the feed water heater. And E sub E is the amount of energy produced in kilowatt hours. In this example, we'll use a time period of 1 hour. To find E sub S, we need to know the temperature and pressure of the steam that entered the turbine. We also need to know how many pounds of steam entered the turbine in the hour we're considering. The steam that entered the turbine was at a pressure of 2,450 PSIA and a temperature of 995 degrees Fahrenheit. That's 5 degrees below what the turbine is designed for. 1,170,000 pounds of steam entered the turbine in that hour. Knowing the temperature and pressure, we can look up the enthalpy of the steam. The enthalpy of the steam is 1,456 BTUs per pound. Now that we know how much energy was contained in each pound of steam, we need to find how much energy was in the steam that entered the turbine. So, we multiply 1,170,000 pounds of steam by 1,456 BTUs per pound, and we get 1,703,520,000 BTUs for the value of E sub S, which is the amount of energy that entered this portion of the cycle during the hour we're considering. After finding the value for E sub S, we need to find the value for E sub FW, the amount of energy contained in the water that exited the feed water heater. 1,170,000 pounds of water left the feed water heater that hour. The water was at a temperature of 505 degrees Fahrenheit and a pressure of 2,700 PSIA. Since these conditions are the same conditions that existed in our earlier example, the value for enthalpy also remains the same, 494 BTUs per pound. Multiplying the enthalpy by the number of pounds of feed water that left the feed water heater in 1 hour will give us the value for E sub FW. That value is 577,980,000 BTUs. Now that we have the values for E sub S and E sub FW, we need to find E sub E, how many kilowatt hours were produced in the hour under consideration. In this example, we find that the load remained constant at 167,557 kilowatts for the entire hour. So, 167,557 kilowatt hours were produced. This is our value for E sub E. Our net generation has decreased from 168,380 kilowatt hours as a result of lowering superheated steam temperature. After finding the values for the formula, the calculation can be completed. First, we subtract the amount of energy in the water that left the feed water heater from the amount of energy in the steam that went into the turbine, and we get 1,125,540,000 BTUs for the change in energy that occurs in this portion of the cycle in the 1 hour period we're looking at. Finally, we divide the net generation into the change in energy, and we get a value for the heat rate for this portion of the cycle. The heat rate is 6,717 BTUs per kilowatt hour. If we compare this heat rate with the one we calculated in the last segment, we see that the heat rate we just calculated is greater. The heat rate for this portion of the cycle increased, and that means that this part of the cycle was operating less efficiently during the hour we just considered. When a portion of the plant cycle operates inefficiently, it affects the overall heat rate of the plant, and the entire plant operates less efficiently. The result is that more fuel would have to be burned to produce the same amount of electricity. We've looked at how one factor at one point in the plant cycle affects the heat rate for an isolated portion of the cycle and thereby influences the heat rate for the entire plant. Now is a good time to review this material in your text and answer the questions. When we come back, we'll examine how heat rate is affected by another factor in another component of the same portion of the plant cycle. In the last segment, we talked about changes in superheated steam temperature. We told you that a decrease in superheated steam temperature causes a plant's heat rate to increase, and the plant operates less efficiently. In this segment, we're going to talk about another factor that influences heat rate, condenser vacuum. We'll talk a little about how a vacuum is formed inside a condenser, how it's measured, and how changes in vacuum affect a plant's heat rate. By now, you're probably already aware of how a condenser fits into the plant cycle. A condenser is placed in the plant cycle so that steam exiting the turbine enters the condenser. Steam entering the turbine is at a high temperature and pressure. As it flows through the turbine, the thermal energy in the steam is converted into mechanical energy that operates the generator. As its energy is converted, the steam's pressure decreases so that the steam exits the turbine and enters the condenser at a low pressure. Inside the condenser, the steam is condensed back into water. As the steam changes state, its volume rapidly decreases. The rapid decrease in volume maintains a pressure in the condenser that is below atmospheric pressure. When pressure drops below atmospheric, a vacuum exists. As pressure continues to decrease, vacuum increases toward what's called a complete vacuum. In a complete vacuum, there is zero pressure exerted. In other words, all the molecules of air have been removed. But as you probably already know, it's impossible to achieve a complete vacuum. There's always some molecules present to exert pressure. This holds true for a condenser. There's always some pressure caused by the air and steam inside it. As an operator, it'll be your responsibility to help monitor condenser operation and make sure that steps are taken to correct any changes in pressure that could indicate a decrease in the efficiency of your plant. Instruments that measure vacuum inside a condenser are commonly used in plants. These instruments are called manometers, and operators monitor them to determine if the correct pressure inside the condenser is being maintained. This is a manometer that measures condenser vacuum in inches of mercury vacuum. One end is connected to the condenser. The other end is inserted into a container of mercury. In this way, atmospheric pressure pushes down on the mercury in the container, trying to force it up into the tube. However, since it's impossible to reach a total vacuum in the condenser, there is some pressure being exerted. This vacuum pressure pushes on the other end of the tube, opposing the pressure exerted by the atmospheric pressure. Now, if the condenser is shut down and vented to atmosphere, pressure is balanced at either end of the tube and no mercury flows into the tube. The manometer reads 0 inches of mercury vacuum. As the condenser is started up, pressure begins to decrease in the condenser. The atmospheric pressure pushes down on the mercury in the container, and the mercury begins to flow from the higher atmospheric pressure toward the lower pressure in the condenser. The mercury rises in the tube. If atmospheric pressure is at 14.7 PSIA and pressure in the condenser is at 10 PSIA, the manometer would read 10 inches of mercury vacuum. As pressure in the condenser continues to decrease, the mercury in the tube continues to rise toward a reading of 30 inches of mercury vacuum, which would be achieved if 0 PSIA could be reached. Now, this is the reading you would get only if atmospheric pressure is at 14.7 PSIA. If atmospheric pressure changes, so does the reading in inches of mercury vacuum. In order to compensate for variations in atmospheric pressure, readings from manometers measuring condenser vacuum in inches of mercury vacuum are used in conjunction with barometer readings measuring atmospheric pressure in inches of mercury. Manometer readings are subtracted from barometer readings to get an accurate measurement of the pressure in the condenser. The difference between the manometer and barometer readings is called back pressure. Typically, a power plant control room will have a barometer indicating atmospheric pressure and a manometer that reads inches of mercury vacuum. In addition, there may be a gauge that is connected to both instruments in order to display the difference between the two measurements, the back pressure in the condenser. The lower the back pressure, the greater the condenser vacuum. Thus, heat rate decreases. Therefore, if back pressure increases, heat rate also increases. The plant is less efficient. For example, steam usually enters the turbine that we've been using as an example at a pressure of about 2,450 PSIA at 1,000 degrees Fahrenheit. At this point, the heat content, or enthalpy, is 1,459 BTUs per pound. Under normal conditions, back pressure in the condenser is about 2 inches of mercury, or about 1 PSIA. Steam exits the turbine and enters the condenser at 102 degrees Fahrenheit and contains 1,106 BTUs per pound. The difference in enthalpy, 353 BTUs per pound, is used to produce the 168,380 kilowatt hours of electrical energy that we saw earlier. Now, if back pressure rises to 4 inches of mercury, the pressure in the condenser is about 2 PSIA, and the steam contains 1,116 BTUs per pound at this point in the cycle. Now there are only 343 BTUs per pound left to produce electricity and net generation drops to 165,600 kilowatt hours. We can see how this increase in pressure affects heat rate in this portion of the cycle if we apply the formula for heat rate, E sub S minus E sub FW divided by E sub E. We'll assume the only value that is changed from design is net generation, or E sub E. So we can use the values we previously calculated for E sub S and E sub FW. We found that 1,707,030,000 BTUs of energy enter the turbine in 1 hour, our value for E sub S. The value for E sub FW, the amount of energy contained by the water leaving the feed water heater, is 577,980,000 BTUs. Net generation has decreased from 168,380 kilowatt hours to 165,600 kilowatt hours. Working through the first part of the equation, E sub S minus E sub FW, we find the change in energy to be 1,129,050,000 BTUs. Next, we divide the change in energy by E sub E, the net generation. We find the new heat rate to be 6,818 BTUs per kilowatt hour. Heat rate has increased from 6,705 BTUs per kilowatt hour, a difference of 113 BTUs per kilowatt hour. Thus, the overall heat rate of the plant increases and plant efficiency decreases. In addition to monitoring pressure in the condenser, it may be your responsibility as an operator to determine possible causes for a decrease in vacuum. Since the vacuum in a condenser is dependent on the rapid decrease in the volume of the steam as it's condensed into water, it's important to make sure that condensation is occurring at a sufficient rate. Condensation depends on the amount of heat transferred between the steam entering the condenser and the water flowing through the condenser tubes. As you probably already know, the more cold water that flows through the condenser tubes, the more heat is removed from the steam. As more heat is removed from the steam, condensation increases and vacuum increases. On the other hand, if flow rate decreases, less heat is removed from the steam, condensation decreases, and thus vacuum decreases. When vacuum decreases, heat rate increases, and the plant operates less efficiently. As an operator, it's therefore important for you to check the flow rate of the water through the condenser tubes. To check flow rate, pressure readings must be taken for the water entering the condenser and the water exiting the condenser. There are usually pressure indications at the condenser water box inlet and condenser outlet. The difference between the two readings should be within the operating range of the condenser. Besides checking flow rate, the amount of heat transfer that is occurring inside the condenser should be checked. This is done by taking temperature readings for the water entering and leaving the condenser. The difference between these two readings will give you a good indication of whether or not heat transfer is occurring properly inside the condenser. The water level in the hot well of a condenser should also be checked. The condensate that is formed in the condenser falls into an area at the bottom of the condenser that is known as the hot well. A sight glass is provided to take a level reading. The normal level of the water in the hot well is maintained by a control system within the unit. Any variation from that level is an indication of a problem. If the water level is too high, condensate may be flooding the lower condenser tubes, thus reducing heat transfer, because the heat in the steam can't reach those tubes. On the other hand, a low level in the hot well is also a problem. If the level is too low, steam could be drawn into the condensate pump. In this case, the condensate pump won't function properly because it is not designed to pump steam, and it could be damaged or destroyed. Besides temperature, pressures, and water level, a condenser's air removal system should also be checked. As you probably already know, a condenser's air removal system removes non-condensable gases that remain in the condenser when steam is condensed into water. If not removed, these gases would exert pressure inside the condenser and cause the pressure inside the condenser to increase and its vacuum to decrease. Also, the non-condensable gases interfere with the heat transfer process. If allowed to accumulate, these gases will blanket the condenser tubes and prevent steam from reaching them. This reduces condensation of the steam, which again contributes to an increase in heat rate. For this reason, it's important that the condenser's air removal system operates properly. We've seen how an increase in the back pressure of a condenser can cause an increase in a plant's heat rate. Next, we'll look at one other factor, which we discussed earlier, that can influence the heat rate of a plant: feed water temperature. But for now, review the material in your text and answer the questions. Your instructor will help you with any problems you may have. So far, we've looked at how turbine supply steam temperature and condenser vacuum affect a plant's heat rate. Earlier in this unit, we mentioned another factor that can influence plant efficiency and heat rate: feed water temperature. Next, we'll take a closer look at the effects of feed water temperature on heat rate. Feed water heaters are used in the plant cycle to increase the temperature of feed water before it returns to the boiler. The closer the feed water temperature is to boiling when it enters the boiler, the less energy is needed to convert the feed water to steam, and as a result, the plant's heat rate decreases. Therefore, it's important that the feed water temperature be kept as close to boiling as possible. However, it must not be allowed to actually boil in the feed water heaters. Condensate, booster, and boiler feed pumps are not designed to move the steam-water mixture that occurs as a result of boiling. If this mixture is pumped through the system, the pumps could be damaged. On the other hand, if feed water temperature decreases, more energy is needed in the boiler to heat the water to boiling. Efficiency decreases, heat rate increases. Let's look at two examples of a change in feed water temperature: a decrease and an increase, and how they affect heat rate. We'll use our formula E sub S minus E sub FW divided by E sub E to calculate heat rate. And we'll assume our values for E sub S and E sub E will remain the same in both examples. First, let's see what happens to heat rate if feed water temperature decreases from 505 degrees Fahrenheit, the design temperature, to 475 degrees Fahrenheit. Again, we're going to consider a time period of 1 hour. Putting the values into the heat rate formula, our value for E sub S is still 1,707,030,000 BTUs. The value for E sub FW is calculated by multiplying the enthalpy of the water at 475 degrees Fahrenheit, which is 457 BTUs per pound, by the amount of feed water leaving this portion of the cycle in the 1 hour period, which is 1,170,000 pounds. The value then for E sub FW is 534,690,000 BTUs. Now, applying our calculation, we get the change in energy, E sub S minus E sub FW, which equals 1,172,340,000 BTUs. Next, E sub E, the net generation, which is 168,380 kilowatt hours, must be divided into the change in energy, which gives us a heat rate of 6,962 BTUs per kilowatt hour, an increase of 257 BTUs per kilowatt hour from the design heat rate of 6,705 BTUs per kilowatt hour. Decreasing feed water temperature increases a plant's heat rate and lowers efficiency. Now, let's take a look at what would happen if we could increase feed water temperature to 540 degrees Fahrenheit. Although it would be difficult to increase feed water temperature above design, we can illustrate the results that a temperature increase like this would have on heat rate. The value for E sub S remains the same. The enthalpy of the feed water at 540 degrees Fahrenheit is 537 BTUs per pound. Again, we multiply this by the number of pounds of feed water that exited this portion of the cycle in 1 hour. Our value for E sub FW is now 628,290,000 BTUs. Therefore, the change in energy, E sub S minus E sub FW, is equal to 1,078,740,000 BTUs. Dividing by E sub E, the net generation of 168,380 kilowatt hours, we find a heat rate of 6,407 BTUs per kilowatt hour. This heat rate is 298 BTUs per kilowatt hour lower than design. As you can see, an increase in feed water temperature causes a decrease in heat rate. As an operator, it will be your responsibility to monitor conditions in the feed water heaters in your plant so that any abnormalities in operating conditions can be detected and proper steps can be taken to return things to normal. Most feed water heaters use the shell and tube design to affect the heat exchange process. Feed water flows through the tubes, and extraction steam taken from the turbine flows through the shell. Heat is transferred from the steam to the feed water. Your plant has normal temperatures and pressures for both feed water and steam in the feed water heaters. You should be aware of what these normal conditions are so that any variations can be detected and proper steps taken to return things to normal. Another important indication of operating conditions is the water level in the feed water heaters. As the heat exchange between feed water and steam takes place, heat is removed from the steam and it condenses. The condensate collects at the bottom of the shell and the level is indicated by a sight glass which is attached to it. Your plant has specified levels for each feed water heater, and as an operator, you will monitor the water levels in them. Any variation from the specified levels could be indications of a malfunction in the unit. For instance, if the water level is too low, it could be an indication that steam is passing through the shell without condensing. This could mean that the automatic drain valve is not working correctly. Normally, drain valves on feed water heaters open if the level is too high, allowing the condensate to flow out, or close if the level is too low in order to reduce flow. On the other hand, if the water level is too high, it might be an indication of a serious problem in the heater, such as a leak in the tubing part of the feed water heater. Again, as with the condenser, the water would blanket the tubes in the heater and reduce the amount of heat transfer between the steam and the water because steam is prevented from reaching the tubes. Well, we've seen what heat rate is, how it's used to measure plant performance, and some things that can influence heat rate in the plant cycle. As an operator, it will be your responsibility to help maintain the proper heat rate in your plant. Superheated steam temperature must be watched, as well as condenser back pressure, steam and water temperatures, and pressures and water level in feed water heaters. The goal of your power plant and your goal as an operator is to produce electricity as efficiently as possible. By paying close attention to all the indications of operating conditions in your plant, reporting any abnormalities to your supervisor, and doing what you can to correct them, you can help keep heat rate in the plant cycle to a minimum.